again. So good morning. Wow, we've got an awake crowd at 10:15 in the morning. This is fabulous. My name is Matt Ayers. I'm a program manager at Microsoft in the Windows Client Performance Group, and I'm going to talk today about performance improvements we've made for Windows Vista. So if that's not what you're expecting, now would be a good time to go. So what am I going to talk about today? I'm going to start by talking about the problems that we addressed in Vista, things that we saw in XP that we didn't like so much. Then I'm going to spend the rest of the talk talking about what we did. We rewrote the memory manager. The new memory manager is called Superfetch. We're leveraging flash memory in the platform and avoiding the disk bottleneck. And then finally, we have some supporting infrastructure that we've built in to be smart about hitting the disk and analyze when things have gone a little off the rails. There are three things I'd like you to get out of this talk today. One, I'd like you to know what problems we were addressing in XP. Not just the symptoms, but actually what was causing them. Second, I'd like you to know which features. That's really the bulk of the talk. What have we done? And then finally, I'd like you to remember and take away how these features work together to give users a consistently performing operating system with Windows Vista. So what causes inconsistent responsiveness? Apologize, I'm not used to the wired mic. I'm going to bring this out here. The first thing that we see that causes inconsistent responsiveness is memory issues, having the wrong contents in memory. And that means when you launch an application, you have to pull it off of disk. Memory may be full, so you have to page things out from disk. You're booting up, so everything hasn't gotten off a disk yet. You've noticed me mentioning the word disk a lot. That leads to the second thing that causes performance issues. And that's random and blocking disk operations. Blocking disk operations, page faults. You don't have enough memory, you page things to disk, you page things from disk. Having program loads where the memory has the wrong contents, you're pulling things off of disk. So what this does is combines to form what we refer to in the industry as the disk bottleneck. And the disk bottleneck is driven by the seek problem. Hard drives are great. Hard drives have gotten so much better over the last 5, 10, 15 years. They've gotten larger. Sequential access time has gotten better. They spin faster. The one thing that it's very difficult for drive manufacturers to address is random I/O. And that's because of the physical nature of disk drives. To service a random I/O, you have to move the disk head. And that disk head can only be moved at a certain rate. So even though we can get throughput speeds that are really impressive, as we go to ATA33, 66, to SATA, and we spin the disk faster, we're still only getting 10 to 12 milliseconds on average for random I/O. Now, to put this in perspective, talking with folks at IDF, and the statistics that they said is, well, processors have been doing great over the last 12, 15 years. Moore's Law, we're 30 times faster in just raw compute power. Disks and random seeks have improved roughly 1 to 1.5 times. Let's think about that. That means that if you had a task in the early 90s that was 5% disk bound, of all the time it spent doing whatever it was doing, it hit the disk 5% of the time. That means that today, with processor improvements and disk improvements, it would be 50% disk bound and spend half of its time servicing I/O requests. We see this as something which is suboptimal for the users, and we want to do something about that. So what about sequential operations, like loading DLLs off of disk? Even things that we think about as sequential under the hood, or think about as sequential and atomic, under the hood, are really random. Let's think about loading a DLL off of disk. And this is using the best defragmentation software out there. This is a perfectly theoretical DLL on disk. Well, you need to know about the metadata, which means hitting the master file table, and there's a seek, because you want all of that lumped for other reasons. You want to know where that DLL is, so you hit the directory entries, and you want those lumped on disk for other reasons. Then you actually get into the PE header, and then you seek back to the data pages and have a lot of micro-seeks between data and text pages. So you can see that even for something atomic, like reading a DLL, you got a lot of seeks. And keep in mind, 10, 12 milliseconds, suboptimal. And then you look at something like Outlook or IE, hundreds of DLLs. Given the mechanical nature of hard drives, we can't avoid those seeks. I just noticed the transition was different on the monitor here and the monitor up there. It was a little distracting. So the other thing is the write side. So reading, a lot of seeks. Writing, same thing. Because of the transactional nature of a lot of our writes, putting something into the registry. You want to write the data, complete the transaction, write a log. So even a registry entry, 5 to 6 random seeks. And then there's page faults. And page faults are, you get kind of double damage there. Not only are they random, they're blocking, because you don't want to do anything until you get the right contents into memory. How does this translate to users? Users see slow. How many of you guys have seen slow? Show of hands. Okay, good. I've got an interested audience. You have slow state transition. Boot slows down. How many are familiar with the term win rot? This is what we use. Maybe it's an internal term. Over time, you get more startup applications. You get more things in the disk. Things get more random. Boot gets slower. Slow is bad. That's why I joined the perf team. I don't like slow. I like having a fast machine. So also, when you're under memory pressure, remember the blocking reads. And then finally, you have slower program launch. The more you have to pull off a disk, the slower your machine is going to be. Okay, so we've outlined the problems, and I think everyone here is... how many folks here are IT pros? And how many are devs? Okay, I just wanted to know, are you feeling the pain individually or multiplied by your entire user base? And so, what were we going to do for you? We rewrote the memory manager. The XP and previous memory managers are really written for memory-constrained systems. 64 meg, 128 meg. The operating system took a lot of that. Applications took a lot. And you find yourself needing more memory and not having the physical memory. Physical memory was expensive. That's changed in Vista. In Vista, you have 2 gig machines, 4 gig machines. Occasionally you'll fill that up, but a lot of the time that's empty. We rewrote the memory manager to leverage that. We're going to avoid hitting the disk where possible. We're going to try and get the right contents into memory. We're going to leverage flash memory in the system to provide a secondary cache that is faster than the disk. Finally, if you do hit the disk, we're going to make sure you hit it in a smart way, and that user applications are prioritized over background tasks, like defragmenting the disk, indexing your search, and other applications that are important, but not right now. And then finally, if things really do go all the way wrong, and you do have a performance problem, we have new diagnostic tools that will report up to users and to IT administrators what Vista thinks is going on. So let's start with smart memory management. And this is Superfetch. So what happens in Vista? I show up at 9 o'clock in the morning. I log in. OS is sitting around. All the startup apps fire. And on my 1 gig machine, a couple hundred megs used there, plus or minus. And 800 megs of empty. That means that anything that I want to do needs to come from the disk. So I'm going to log in. I'm going to launch Word. Okay, I came off the disk. It wasn't super fast. And I'm going to launch Outlook. You're seeing a pattern here, right? Internet Explorer. I'm going to launch my photo editor. So I've now pretty much filled up memory, and this is what I do during the day, and I've got everything running. But now, one thing you may notice is that some applications, if you launch them the first time, you launch a web page like IE, and you browse your page, you close it and launch it again, it's faster. That's because this is what happens when we quit IE. We take that memory, but we don't go and erase it. It's not like a whiteboard. We keep it around on the standby list. We keep it in a memory cache. By keeping it in a memory cache, the next time you run it, if you haven't run anything else, we pull it straight from RAM into RAM. We just transfer the necessary bits from the standby list back into active and working memory. So that's an important point. Moving things from a memory cache into the working set is really, really efficient. So that's the foundation of Superfetch. Get the right contents into the memory cache so that users have a consistent experience. Now, the memory cache, there's no penalty for giving that memory cache memory to somebody else. If instead of launching IE again, I decide to launch Visio, that's fine. It's just like if the memory was zeroed. We're fine giving that away, but we may get lucky, have a hit in the memory cache, and give a better user experience. So Superfetch, to make this more effective, watches what users do. It knows that on the weekdays, Matt logs in at about 9 in the morning, launches Outlook, launches Word, launches IE, that there's a pattern there. He works until noon or so, goes to lunch, 1 to 6 uses those same applications. On the weekends, it's a whole lot more Civilization 4, Age of Empires, a lot less of the work applications. So we track users' behavior. And this, one thing I want to make very clear, we're doing this on a page level. What memory pages are pulled off of disk and into RAM. We're not tracking by applications. There aren't privacy concerns. We're just looking at this at a very low page-based level, even though a lot of the descriptions I use applications to make it a little simpler. So now that Superfetch knows what I'm doing and when I'm doing it, what does login look like? I log in. Right before I log in, Superfetch pulls these applications off disk into the memory cache. And it's a best guess. So, but if I decide, oh, I'm going to go and run my photo editor, it comes straight out of memory. No delay, no hitting the disk. By having the right contents in memory, we avoid the disk bottleneck. Getting the right contents in memory is great. Keeping it there is also important. One thing we've heard a lot from our users is, well, yeah, it's good. I launch my applications, I go get my cup of coffee, I come back, I start working, I go to lunch, and when I come back, everything is slower. Why is that? Well, we'll take a look. Here's what happens at 12:10. You've locked your machine. Windows knows that you're idle. And in XP, the IT administrators in the group know that idle tasks kick off. This could be inventory software. These are line of business apps, things that run in the background to keep your machine running the way that you, as an IT administrator, want it to run. So when the idle task requests a memory, what happens? Well, in this example, when I logged in, I first launched Word, then Outlook, then Explorer, and then my photo editor. And that's the order in which I used them to keep things simple. So the oldest application in memory is towards the bottom, Microsoft Word. The XP Memory Manager gives away memory pages and pages things to disk based on the least recently used page. That means that when the idle tasks start up, we page Word's pages to disk and give that to the idle tasks. Now more idle tasks fire. What memory does it give away? Well, the newest thing in this stack is the idle task, so we're not going to give that away. Outlook is now the least recently used, so we consume that, and that goes to disk. You're beginning to see where this experience is going to go when I come back from lunch. The idle tasks finish. Great. Well, what should we do when the idle tasks finish? Y'all remember a few slides ago? That's right. We put the idle tasks into the memory cache because they're the most recent. Well, that's good as a generic algorithm. It helps you with your IE. It does not make you happy at 1:05 when you get back from lunch, you're late from a meeting, and you need to print something out of Outlook, which is busily paging back into memory. We recognize this in Vista, and we've done two things to help. One, when the idle tasks run, did I just double click? No, I just had a slide goof. It picks the application you're least likely to use. So if you infrequently use IE, idle task will replace IE. Then, as idle tasks quit and new ones start up and request memory, Superfetch knows that the idle tasks aren't nearly as important to this user as Outlook or Word. So it keeps idle tasks confined to we're not going to use the entire memory, we're going to use a much smaller set, especially if these idle tasks are marked as low priority. Finally, all of the idle tasks finish. We have some memory available. What are we going to do with it? Superfetch is going to look at usage patterns and say, you know what? Initially, we're going to give it to the idle tasks. But as the user comes back from lunch, as it nears 1 o'clock, Superfetch knows that IE is much more likely to be used than the idle tasks, which typically run at noon. So it pages IE back into disk, and when you, the user, get back from lunch, your machine is as responsive as it was when you left. So I've talked a lot about how we're getting the right things into memory off of disk, how we keep the right things in memory. there's a lot of question of, well, you still have to hit the disk, right? Yes, we are hitting the disk, but we're using low priority I/O. And low priority I/O steps out of the way and gives user applications priority. So you go to lunch, you come back early, and Superfetch is paging IE in. If you log in and do something that's disk intensive, Superfetch will step back and get out of your way. It may be IE, and it may not have finished putting things back in, paging things back into memory. It just means it's going to be a little bit slower. But on the whole, we are much more consistent for responsiveness than we were in XP. The last bullet on this slide is really important. I've talked about how Superfetch takes data from a slow storage, like the disk, and moves it to something really fast, like RAM. Well, we'll move it from slow to any speed. For example, non-volatile RAM. So if you have a source of non-volatile RAM in the system, like a hybrid hard drive, a ready drive, or a USB key used for ready boost, we have other sources of cache. And Superfetch is the secret sauce that makes that happen. So how do we use Flash to avoid the disk bottleneck? First, it's ready boost. Ready boost is this guy. It's a USB key. How many people are carrying one right now? It's a pretty good. How many would have answered yes a year ago? A lot fewer hands. Flash drives are becoming cheaper, more available, and larger. Flash drives also, as we saw earlier, are 10 times faster at satisfying random reads than a hard drive. This means that we could use this as a cache to give you more consistent performance. What does this mean? What happens when I take a USB key and I plug it into the machine? And I'll show you a demo in just a minute. As soon as I plug a USB key in the machine, I can show you what it looks like for the first time. I'll plug this in. Actually, I won't show you what it looks like for the first time. We'll imagine. Because switching back and forth, I want to do as little as possible. The first time you plug it in, you get an autoplay dialog. You're very familiar with these. It says, do you want to view media, watch your movies? Do you want to listen to your music? Or do you want to use this to speed up your system? If you select speed up your system, another dialog box comes up. It says, well, how much of the device do you want to use? After you make that decision, you're done. The computer will use this device for ready boost forevermore until you tell it not to. So once a ready boost enabled device is plugged into the computer and configured, Superfetch says, okay, I've got a cache. I'm going to fill that proactively with data that the user is likely to need. So I plug in my 512 meg key that I've decided to use the whole thing for cache, and we fill up 512 megs of data. Well, that's not really true. We fill up a gig of data because we compress. So we now have a gig of pages that the user is likely to use. That's good, but that'll probably include some boot things and some startup apps and things that happen regularly but don't get used all the time. So we also track the user's actual use. Whenever you page something or write a small piece of data to disk, after that write's completed, it gets cached into the ready boost device. If you read something off of disk, for example, if you page an application off of disk, that also gets cached into the ready boost device. So we start by being proactive, filling the secondary cache with what Superfetch thinks you're likely to need. Then we track what you're actually doing. And the best way to show this is with a demo. And I think I might be a little out of order, but I think I'd rather show you what we're doing and then talk about why it's so great. I'm going to start by just launching a set of applications. And this simulates a user's daily work. We're going to launch Outlook, we're going to launch OneNote, Adobe Acrobat Reader, and PowerPoint. These applications, what we've done to make it consistent is clear out the standby list. So this is as though you were pulling things off of disk, for example, in a paging or a low memory situation. And this way we can compare apples to apples and show the real effect of using Flash as a cache in the system. So we launched OneNote, and again, what's happening is everything is being pulled off of disk here. And that's one thing that, as this launches, I want to talk about. It's kind of hard to demo our performance features. They're layered. We have Superfetch, which is trying to get the right things into memory. We've got Ready Boost, which has a second layer of cache. We have low priority I/O. We still have the XP app prefetching. So there's a lot going on. And to demo, I want to make sure that I can isolate. This is what this feature does. So it took about 30 seconds. And it's important to look kind of at the total, because you track buffer in the drive, other DLLs being in memory. This will vary a little bit from run to run, computers being non-deterministic for you computer science majors in the audience. So what happens when you throw a ReadyBoost device in? What I have here is an app that we use to test performance and measure performance. I'm going to plug the ReadyBoost device in. You'd hear the standard, the USB noise if I had audio out. And up comes the window that shows it's a drive. This is a drive. You can see I've got my slides on here. I've got a couple of applications. This can be used as a ReadyBoost device as well as a store for your files. So what happened when I plugged that in? Well, you can see here that this green line, which represents the amount of flash memory available for ReadyBoost, jumped up to 800. It's kind of hard to see that on the monitor. But because we're compressing, remember, my 400 megs of physical cache gets doubled. It thinks about it for a while. It asks Superfetch, what's Matt likely to need? Matt's likely to need probably Outlook, OneNote, PowerPoint, and Acrobat. And as soon as ReadyBoost and Superfetch finish talking, ReadyBoost starts to populate the flash drive. And you can see that this happens fairly quickly. Not quickly enough. It's still a lot of time to talk about what's going on as this trends towards the bottom. But as soon as this hits 0, it means that I've filled the ReadyBoost with what Superfetch is likely to need. And now, I'm going to double-click on the Run with EMD. The old code name for ReadyBoost was EMD. So I'm going to double-click. And we're going to run the same set of applications. The only difference between these two runs is it's going to show up in a different column. And so you can see that with having ReadyBoost enabled, it's a little faster. Oh, very little faster. But remember, this is best guess. And I imaged this machine right before leaving for TechEd, so I haven't even had a full week of use. So it's best guess. It's still doing all right, even though it doesn't have a lot of history. But it's not reacting to what I'm doing. It's reacting to what it thinks I'm going to do. So you can see we've got a little bit of an improvement. We're twice as fast on OneNote. You'll also notice that the Office applications are getting progressively faster. It's because they share DLLs in memory. I'm not picking on Outlook. It just happens to be the first on the list, and it's taking the hit for a lot of the DLLs that get loaded. So that's a little bit faster. That's good. No one would complain about being 10, 15% faster. Let's run it again, because now it knows what I actually do. It's watched me through my fictitious day, and it says, okay, he's likely to need these applications. And as I rerun it, things get a lot better. We're twice as fast. We're avoiding the disk bottleneck. Almost everything right now is coming off of flash. You can see we get real improvements as soon as you start using a computer that's ReadyBoost enabled. It's faster. This is just the coolest thing to me. It's amazing. You can stick in a USB device. You can, if your parents are saying, boy, I'm seeing a lot of swapping, or whatever relative is not quite as technically competent as you'd like, tell them, head down to Fry's, pick up this USB key. Here's the effect you're going to have. You'll be twice as fast. So, no applause, nothing? Thank you. So I'm going to do one more demo, and then I'm going to talk about some of the frequently asked questions we have, because you all know that that USB keys can walk away. I'm going to run this again, because there was actually fairly recently a press article that said, I'm a little concerned about ReadyBoost because these keys can go away, right? What's the performance going to be like if you're running with ReadyBoost and things are going along and all of a sudden somebody just pulls it out? Is it resilient? What's going to happen? Is it going to have to refill memory? How does the system react when ReadyBoost goes away? It just goes back to what it was before ReadyBoost was used. There's almost no delay. It doesn't have to tear down a cache. It handles the surprise remove event elegantly. It just keeps working. So that's the end of the demo for ReadyBoost. And you guys don't need to see the rest of that. I mean, you can. There's nothing secret about it. It's just a bunch of slower applications. So, all right, I'll show you. Just see? Nothing secret. Nothing, just slower. So ReadyBoost, what are some of the characteristics? Well, as you saw, ReadyBoost is reliable. It's robust. It can handle the surprise remove event. Well, the surprise remove event gets a lot of people thinking. Okay, so as we learned earlier, ReadyBoost doesn't have any unique content on disk, on the ReadyBoost device. Everything that's cached has a backing page on disk, whether that's in the page file, whether it's a code page, a DLL, whatever you have. But someone just walked away with the contents of memory. That would make me nervous if I wasn't working on the feature and knew that we had thought about it. What we do is we encrypt everything before it leaves the main board. That we use AES 128 to encrypt the data, and we use internal compression algorithms to give us that 2-to-1 compression. So there's a little bit of processing that goes on before the data ever hits the ReadyBoost device. That means that even if someone walks away with your USB key, your data is secure. Also, people think, okay, then you're encrypting and you're compressing, and isn't that slow? It's not. All the performance numbers that I'm giving you here today take into account compression and encryption. So it's not like it's not the $19.99 plus sales tax, shipping, and handling. Everything, all-inclusive price, 10 times faster than a random read off the hard disk. So we talked about removing, we talked about encryption. What about device wear? Well, ReadyBoost is exposed to the operating system as a volume. This means that ReadyBoost is able to leverage all of the wear leveling algorithms that exist in the flash drive. So even if we just did that, that would be good. We're not circumventing the flash manufacturers who know best. But we can be even smarter. Most of our writes are 4K, especially if we're doing a lot of paging. Most block sizes on UFDs, on flash drives, are 64 or 128K. That means that to do a 4K write, you actually read 64K off the disk, change the 4K in memory, erase the cell, and then put it all back onto disk. And so for a 64K block, that means you're doing 16 operations to fill 64K with 4K blocks. Sorry, 16 erases to fill that. We can do better. What we've decided to do is cache writes up until they hit 512 megs. Once we, or 512K, I'm sorry. A couple people, I saw eyes go, blunk. That means you're listening, that's great. 512K blocks. 512K is a multiple of most, if not all, block sizes in UFDs. That means that whenever we write to a UFD, we do a single erase and then a write. So that further lengthens the life of the UFDs. And as you can see on the slide, we're guessing about 20 years up to a couple millennia. And I'll be in the TLC afterwards if folks are concerned about that. After 2 millennia, no. But I will be after this talk. So we've talked about that. The last question, and I apologize, I don't have a slide on this, but people ask, what are the performance requirements? You need to have throughput of 2.5 megabytes per second for 4 kilobyte random reads, and 1.75 megabytes per second throughput for 512 kilobyte random writes. Now, at the end of this slide, I have some resources on the resources that we've documented where you can find these, as well as what tools you can use in Windows to measure that. Finally, I got an email, it was a couple days ago, and someone said, Matt, I saw this article in PC Magazine about UFDs being, well, the wrong form factor for laptops. They stick out, you walk in, you bump them into something, they tear off, it's a connector that can be weak. Are you guys doing anything about that? And I love getting those emails because I can say, yes, we are. Not only, I talk about UFDs, that was the original concept. Then I started walking around with one on my laptop and found that it's not convenient. We opened it up. We now support SD, compact flash. We support Sony memory stick. If somebody wants to build it into the laptop, we'll support that as well. So any flash device that's on a bus that is fast enough to meet the performance numbers I quoted earlier will be used as a ReadyBoost device. The last thing to think about in terms of Ready Boost is that in beta 2, we had some bus checks that were suboptimal. So if you put your SD card into a beta 2 machine, even if you have a machine running Vista beta 2, even if you have a bus that's fast enough, it may not recognize it. In the resources slide is a link to a registry key that you can set to make it work on beta 2. For RC1, any flash device that is fast enough and on a fast enough bus, which is everything faster than USB 1.1. USB 1.1 is not supported, unfortunately. It didn't make the cut. It will recognize that device. So memory sticks, SD, compact flash, whatever you would like. So that's an awful lot about Ready Boost and its read caching properties, how we can avoid the disk by putting recently and frequently used data into a compressed, encrypted, efficient cache. That's the demo I just did. Now let's talk about the Ready Drive hybrid hard disk. That's the other side of the equation. What about write caching? What about booting? How can you use non-volatile flash memory to improve other aspects of the system now that you've taken care of read caching with Ready Boost? What we can do is, in addition to the track buffer, which is volatile and handles, it's a small area to handle very recent writes and other disk accesses, we can put a larger cache in to handle not only a larger non-volatile cache in to handle other operations. So you guys remember the DLLs on disk picture, where we've got data pages, text pages, PE headers. We have to have seeks because of the organization of the operating system. And I've just put each color as a different application. So you got the orange app, you got the green app, and you have the black representing the rest of the entries in the master file table. If you have non-volatile RAM on that hard drive, if you have a flash cache, you can store those in the flash cache and eliminate all of your seeks. This means two things. One, it means that you don't have to seek. You eliminate that 10, 12 milliseconds, especially on a notebook, right? 12, 15 milliseconds if you're on a 1.8-inch drive. You eliminate that seek. That's good. That just has better, zippier responsiveness. The other thing you do, though, is you don't disturb the write that's currently going on. So let's say that I'm reading off my data pages and I need to get some metadata from the master file table. In the old, using a standard hard drive, that means stop your sequential read, move the disk arm, wait for the platter, read the master file table, move it back. Keep reading your data pages. With the hybrid hard drive, and using Ready Drive, it means read your data pages, service that read for the master file table out of the flash, and just keep reading your data pages. We've just saved 25, 30 milliseconds. So it's not just being quicker than the hard drive, it's letting the hard drive do what it's best at. I think that the holy grail for us, the ultimate goal, is to be able to do single seek technology, where all the media, right, your MP3 files and your videos, things like that, are defragged and aligned perfectly on disk, and everything that would have caused a seek is in the non-volatile RAM. That's a goal. We're not there for Vista, but that's the way to think about it, is how do we put the seeks in the cache and let the disk do what it's best at, long sequential reads. So, talking about the cache, what's in the cache? Take a drink of water. I'm just pausing for suspense. In the cache, we have 32 megs that are used to buffer writes. The slide should read buffered writes. Any writes that go to the disk, we can fill up to 32 megs and then flush that out. The flushing policy is up to the hard drive manufacturer. For our prototypes, we flush when the cache gets down to when the buffer gets down to about 8 megs free. Different drive vendors have different policies. And right now we have both Seagate and Samsung that have announced availability of Ready Drive for systems that are shipping with Vista launch. They will have them available to the system manufacturers. So we cache writes. We also put data, we use the next, say, 64 megs to put in information that'll help accelerate booting and resuming from Hibernate. We saw how by putting the right data in the cache, you can eliminate seeks and let the disk do long sequential reads. That's going to help boot. And we're going to put data in to do that. And unlike ReadyBoost, where the cache is torn down after every state transition, as well as every removal or insertion, ReadyDrive persists across boot, across Hibernate, across standby. So we say in a 256 meg drive, we've taken care of the first 100 megs with cached writes and then boot and resume sectors. We now have 156 megs left over. We split those with our OEM partners. Half of that, so 78 megs, is used for whatever the OEM would like to make faster. A lot of OEMs are opting to use this for media players, their DVD player to have a quicker media experience, MP3 players, their diagnostic applications, whatever they feel would give the best user experience. Finally, the rest of that is used as a read cache. It's similar to what ReadyBoost does, but it's not compressed and it's not encrypted. Keep in mind, neither is the rest of the data on the hard drive. So ReadyDrive is a hard drive. It appears to the OS as a hard drive. So given that we're putting these 4 things into the cache, what does that do for the user? Well, we accelerate state transitions. We also can spin down the disk. And that's really important. A lot of times, whether you're sitting in this seminar or you're on a plane, you're doing activities that may have the computer on, but not necessarily doing read-intensive activity. You're always going to have writes, log files, temp files, transactions. They trickle out. Those will keep the disk spinning. But oftentimes, you don't have a lot of reads. Well, what we can do with a ReadyDrive is we can buffer those writes and spin the disk down aggressively. If the disk isn't spinning, the spinning platter is not consuming battery life. So if it's not consuming battery, you have more to use for screen and all the other parts of the computer. We estimate that we're going to save 20 to 30 minutes of battery life, well, 15 to 30 minutes of battery life, depending on if it's using it normally or sort of the meeting situation where you've got it sitting, but you're not actively using it, by spinning down the platter. Also, if the disk isn't spinning, the disk isn't going to be susceptible to vibration, rotation. You guys there's a lot of IT professionals in the audience, and I'm sure everyone here has witnessed the behavior where users like, I'm done for the day, close the laptop, tuck it under their arm, start swinging it, and you can see the disk light, and it's spinning, and you're just thinking, oh my gosh, the forces that are going on that platter that's spinning at 5,400 RPM, that's an RMA waiting to happen. So if it's not spinning, you don't return RAM because the user's swinging their laptop. We're going to make disks more reliable. And then just a personal benefit, I just like that they're quieter. It's just nicer. So I do have a video of spin down, and I will transfer over to my Vista laptop. And I did this on video so that I could play it back at a faster speed, and I honestly wouldn't have to carry yet another laptop to TechEd from Seattle. So I'm going to double click here. And so I'm playing this a little faster than normal. But what are we seeing up here? We're seeing a user using Word. We're seeing red bars and green bars. Red bars mean that the disk is spinning. Green bars mean that the disk is spun down. The interesting thing about the green bar is the fuzzy text that no one here can read. What that is this says 7.35 megabytes. This says 7.7. This one says 9.4. This is the amount of data written to the disk while the disk was spun down. This is logging, temp files, and the other writes that occur to disk, well, that aren't user-initiated. That being said, if a user saves a file, that'll also be written into the flash. So you can see that in this video, users doing work, they're being productive, and the disk is staying spun down. If the user was idle, if they were watching a presentation or listening to a speaker at a meeting, those green bars would be even longer. The video that I didn't bring, because honestly it's really boring until you know what it is the boot video. We did an experiment where we pinned the right sectors for boot, and we saved 25% of boot time. And I would have shown that video, except it's a black screen for a long time, and then you get the Vista logo, and then you're done. So if you all picture that real quick, and the Vista logo and the Ready Drive is faster. But we are seeing real boot performance improvements. I've got it here if you'd like, but really. So we developed the Ready Drive technology, and we looked at it from a performance standpoint. What's going to be best for the user? And we established that putting the flash next to the drive is going to give the best performance and the best protection for the user's data. That being said, we didn't want to go it alone. This is not a Microsoft says this is what we're doing. We took this to the standards bodies. We have this as part of the T13 spec, and it's the ATA command set with a few additions. You got to be able to tell us you're a hard drive. You have to be able to add things into the pinned set. And pinning is just a term meaning take something from the disk and put it into the flash explicitly. So Superfetch will pin boot and read caching data. OEMs pin their favorite applications. You have to have a facility to say, hey, enter a power saving mode. It's more aggressive than the spin down. And that's really about it. It's been adopted by the T13 command set, and we will be working with the standards body moving forward to make this a part of the compute platform. This is part of the logo program for 2007, Q2 2007. This is a logo requirement for premium laptops. Now, any laptop that has sufficient power will be able to run any SKU of Vista. This is just to get the logoing sticker. Manufacturers will put a Ready Drive inside their premium logoed laptops. So we've talked about ReadyBoost and Ready Drive and how Superfetch populates both of them. A question I get a lot is, do I need them both? Which one's better? Which one should I get? There's only so much flash to go around. What do I do? We recommend both. They serve very different purposes. ReadyBoost is a read cache. It's big, it's compressed, but it's not necessarily trusted across resume, state transitions, and other events. Ready Drive is a write cache that saves battery life, improves boot, and does have a little read cache. We can see in the future, as the caches on Ready Drive get larger and larger, we could use part of that flash as an actual ReadyBoost device. But for the first generation, they're separate. ReadyBoost is really the most effective read cache because you can get the sizes out of it. Ready Drive is really the laptop's best friend in terms of improving battery life, reliability, and performance in terms of boot and app launch. So this is the same thing in text. And they are complementary. So we've talked about how we get the right things in memory, how Superfetch watches the user's actions and is proactive and aggressive about keeping the right things in memory. We've talked about how we can use flash in the platform to improve performance and give a more consistent performance while improving the mobile experience. Well, what happens if you have to hit the disk? If you have to hit the disk, it's slow. And we want to make that better. And we've introduced the concept of prioritized I/O. Because we recognized that even though you can mark a task as low CPU usage, a low CPU task can still do an awful lot of reads and writes. And going back to the seek problem, it makes the system slow. So with this, and these are applications that need access to the disk, like your virus scanners, your disk defraggers, but they don't want to be interfering with the user. They would really rather just kind of get out of the way. And so what we want to do is give application developers a way to say, my application is less important than whatever the user is doing right now. If the disk is idle, I'd like to use the disk. but otherwise, I'd like to get out of the way. And we've done this by creating the concept of prioritized I/O in Vista. And this allows an app developer to say, this is I'm low priority. And so we're doing this, we're consuming our own APIs. Superfetch uses this to pre-populate memory. Search indexing uses this. The new Vista search engine won't interfere with you as it's looking, okay, the Outlook email and these are indexed. It's more efficient about that. Disk defragger, that's also using low priority I/O. And then finally, startup applications. And this one is really exciting to me. When we call this process boxing. We're boxing our startup applications. And that's taking their priorities and lowering CPU, disk, and memory. Lowering memory priority means Superfetch is more likely to give their memory away. So with boxed applications, with standard startup applications, you log into you log into XP, you type your password, and you wait as all the little boxes in the lower right-hand corner of your screen populate with your startup applications. So with Vista, we've put them all in the box. When you log in, they start up at low priority. Now, this isn't the services, right? The actual service doing the virus scanning, the service that's doing work, the scripts that IT professionals put together to make sure that everything is safe and secure, those run at normal priority. These are just the startup applications that are the UI and the interface to these services. And so I'm going to go back and give a demo of low priority I/O. So what I've done is I've taken the same cold start and I've run it because you guys don't want to sit through it. And this is with no competing I/O. There's nothing going on in the system. And Outlook is a little slow. My guess is that that's anomalous. I see this every once in a while in the demo. So I'm now going to run an application that simulates a load on the system. This load could be a defragger running. This load is running at normal priority, and it's really going to do. It's not going to do kind things to the system. Well, how many folks here defrag your hard drive? How many of you do it in the morning while you're working on your PC? Exactly. We've got this class of applications that they're important to have the work done, defraggers, but they generally run at 2 in the morning. I call them vampire applications, and I hope that doesn't offend folks that actually write these applications. They're really useful. I like them a lot. The nature of them, because we haven't done a good job in the OS of providing you a way to get access to the disk during idle times, is that they slow down user productivity. And you can see this right here. You can see that Outlook is taking, 50% longer to start. Another thing I want to point out in this demo, especially because I've got a lot of dead time as we have the competing I/O, the times are just the startup and launch times. So if anyone's out there with a stopwatch timing the launch of OneNote from when you see the splash screen to when you see it quit, you'll notice that it's a lot longer. That's because I'm using some of the accessibility interfaces to manipulate and close the applications. I've introduced delays. So I'm only measuring the time to start up where it's pulling data off of disk or out of the cache, the places where I haven't introduced delays. And boy, when the OS is competing with a workload, it's grim. You know, it has the same pattern, so you know that it's doing the same type of work, but it's fighting with the workload application. This could be a file copy, anything. It's hitting the disk and making your users unhappy. So what I'm going to do is talk about low priority I/O before I finish the demo, because we do have some dead time. How do we implement low priority I/O? It's actually very, very, very simple. We have 2 stacks. We have 2 queues, an I/O queue for normal priority and an I/O queue for low priority. So we've finished here, and we've seen that the under load total is almost double what you had for just the standard app launching. You see that 96,000 units of work were done. I believe that they're 512K blocks. I don't remember what I wrote in there. I'm going to reduce the workload to low priority I/O. This is the same workload. What we're doing is putting it in the box. This is the same thing we've done for startup applications. And now I'm going to run the same demo under low priority I/O. And again, we're clearing the memory content so that everything's coming off of disk, so we have a fair comparison between the three. And yeah, I thought Outlook was a little sluggish that first time, so we will see a bit of an improvement in the Outlook performance. It's not low priority I/O making it faster, it's just getting out of the way. So we should see that the total times are roughly the same between the cold and the low priority I/O. And part of the reason that the Outlook is a little bit higher under cold is because I had let the machine be idle for so long, and so other things kicked in. But you'll notice that the rest of the applications, low priority I/O, the same workload is running, it's still doing work. That second queue is never starved. That's important. We try and clear the normal priority queue first, but we never starve it. So roughly 9 out of 10 I/Os come out of the normal priority stack, and if it's not empty, we service 1 off the low priority stack. So the things to notice here, low priority is much closer to the cold total. It's actually better, but my guess is that we rerun the cold, we'd get roughly identical numbers. Competing I/O is much less, but work still got done, and it was the same application. So if you are an internal developer, an ISV, and you have applications that should run in the background when the user is logged on but not using a given resource, we really encourage you to put them in the box, as we like to say. And the question is, okay, that's great. How many lines of code do I have to change? You know what? I'm going to tell you. 1. 1 line of code. If you write threaded applications and you have a worker thread that's actually accessing the disk, make a call to set thread priority with the new constant thread background mode begin. This will lower your CPU priority, it will lower your disk priority, and it lowers your memory priority in the eyes of Superfetch. If you have a process-based application, if you've got a full app, call set process priority class. So with minimal changes to your code, you can make it so that your application does not interfere with the users. Okay. Having explored how we get the memory contents right, how we use Flash, how we allow developers to appropriately prioritize their disk access, we're still going to have priority problems. We're still going to have random seeks. We want to know where they are. What's causing my machine to start up slowly? What's causing my machine to shut down slowly, my apps to launch slowly? And this is something that we've wanted to know for a long time. But we've got 2 major problems. One, it's not repeatable. Those of you working help desks get a call and say, my machine was really slow when I launched Word. Can you do it again? Well, not exactly. It kind of happens sometimes, but I don't know what it is. It's like, oh my gosh. I really would just like some kind of like a flight recorder or a black box so when it's being slow, the user can go, slow. You want something in the infrastructure that's tracking what the user's doing so you don't have to repeat the events. And then proactive. You know, we log a lot in the event log, but rarely do we bubble that up to the user. And so our first steps to overcoming current tool limitations is improving our infrastructure. And this is with the CKCL, the Circular Kernel Context Logger. This is a system logger that is used to watch what the user's doing and record activity, context switches, disk accesses, and Vista then will analyze this and bubble up the most important events so that users can see exactly what is causing their computer to be slow. And it's an infrastructure piece. It's not something, we're taking the first steps. This lets us put the plumbing in place. Where you'll really see this is in the next few versions. So I guess at the end of the talk, what I'm doing is giving a little bit of a preview for what you'll see, not in Vista, but Vista plus 1. So we're building the plumbing, and then we'll expose that up to the user. So when I started the talk today, and I want to finish in time to leave some time for questions, I said there were 3 things that I'd really like you guys to walk away with. The first being, what are the issues that we're seeing with current operating systems? Not just the symptoms, but what's causing it. And that's largely the wrong memory content and the disk bottleneck. I'd like to talk about what we're doing. I'd like you to take away what features do we have in Windows Vista that address those problems. Those features are Superfetch, Ready Boost, Ready Drive, Low Priority I/O, and the CKCL. Then finally, how do those features complement each other? Well, we've got Superfetch, which is solving the memory problem, putting the right contents into memory at the right time. We have Flash, we have Ready Boost and Ready Drive, which serve as read caches and also write buffers to improve consistency, and then Ready Drive will improve battery life, reliability, and accelerate boot and resume performance. We have low priority I/O that makes sensible access to the disk. Developers can let their applications get out of the way. And then finally, the CKCL will help us track down when there are problems and what we can do about them. So that is the end of the talk. I want to thank you guys for coming. Here's a few resources that will give you some more information. The top two are the ones that are specific to this talk. The top is an overview paper, and the second is an FAQ that I've put together on Ready Boost and Ready Drive. And then finally, before we take questions, I want to encourage you to fill out an evaluation. The evaluations are really important to us. If you like the session, there are eval terminals right out behind you. Rush out. If you didn't like the session, you can get a jump on lunch. So thank you all very much, and I will now open the floor up for questions. The question was, what's the reference PC? I don't have the exact specs. I know it's 512 megs of memory. It's a pretty decent hard drive and a discrete graphics card. But I'll check, and I'll get back to you. See me right afterwards. There's, yes, at the mic on stage left, so you're right.
So one of the performance hits that I resent the most, I guess, in my systems at home anyway, are the kind of things where you have UPS system and the sort of the daemon that runs to keep the UPS going, and some other anti-spyware programs such as CounterSpy from Sunbelt. What they'll do is they'll boot up and load in for every user that logs on to XP. So if I log on, I'll get the power supply software, I'll get the CounterSpy software loading up. If I then switch user, my wife logs on, those daemons start up in her session as well. It seems like they need to run for the machine, not for the user session. So are they just making programming errors, or?
That's a design choice that they've made to run as in user space rather than in the system user as local system or local admin. So if they were to run local system, it'd be available for all. So that's largely a design choice. But if they were to use low priority I/O, not only and run as local system, they could service all users and stay in the background. But that is largely a design choice.
But will Vista make it any easier to program that way, I guess, to write them correctly, I guess?
It will make it easier to use low priority I/O. I can't really speak to the local system, local service.
Okay. Another quick one would be, could you set aside a portion of your system? Would it make any sense to set aside your portion of system RAM to be Ready Boost? To change the change the overall behavior of your system.
That's interesting. Would you set aside a portion of system RAM for Ready Boost? No, because Superfetch sort of serves that same purpose with the standby list and the memory cache.
Okay.
So it's doing the same. It's a good question, but it's doing the same sorts of things with RAM. And because Ready Boost has the back pages on disk, it's better to let Superfetch manage the RAM and Ready Boost independently.
Okay, good. I'm looking forward to this. Sounds
great. Thank you. I appreciate you coming. I'll take a question from the other side.
Sure. On the Ready Drive, you said the OEMs could pin essentially half the cache with their favorite apps. Can I overwrite that in case their favorite apps aren't my favorite apps?
We haven't finished what we're doing with the OEM pinning. We haven't finished the complete spec, but right now it is a registry entry. So if you have access to the registry, you could probably modify that.
And I had a quick one for you on the Ready Boost. Leaving aside USB keys for a moment.
Okay.
It looks like you had a great tool set for determining how much system RAM I actually want for a particular application set. the Mac, to find the most bang for my buck? Are those tools you were using available?
The question is, was the PFUI tool that I'm using available? It's actually, all it's doing is showing me the net memory consumed on the various lists, and unfortunately that is an internal tool. But I will take the feedback back, because one of the things we're looking at is what tools do we provide for vNext? And we've heard this. You're not the first to request the tool set.
It's better, yes. So thanks.
Thank you. I'll just alternate. Yes?
Right, so I'll just re-echo that one. The move to Vista is primarily around performance for us, and needing to be able to demonstrate through a metric that this is how much faster the system will perform. You were doing simple things just in timing, opening, closing of applications. Even something that simple, Microsoft provided, for instance, the BootViz tool to be able to help with slow startup. BootViz was a tool that was
Right.
provided, anything and all around that. One additional thing back on the Ready Boost, you didn't mention a card bus interface. You had PCIe, you had USB. Would card bus adapters be acceptable for use so that it would fit nicely in a laptop?
The short answer is I don't know, but I can give you some guidance. Card bus is certainly fast enough. An external USB reader will not be supported in Vista, the kind that you plug in, and I am going somewhere with this. So the kind where you buy it and you plug it into the USB port, because the drive shows up with no media in it, similar to what your floppy drive does. That gives us all sorts of headaches. So if the card bus reader only exposes the volume when it's inserted and doesn't put itself in the middle of those two, then yes, we will support it. If the card bus reader exposes itself as an entity in that chain, we probably will not.
Perfect. Thank you.
Sure.
Tools.
With,
If you're in line for tools, just raise your hand. Okay. Yes.
with respect to Ready Boost, is more read cache always better, or is there a margin of diminishing utility?
Yes, that's a great question. The range that we recommend for Ready Boost, the low end is a 1-to-1 ratio with your physical RAM. That means that you have a 512 meg machine, 512 meg Ready Boost, you get a gig of cached pages. We see the effectiveness trail off for the current version at about 2.5x. There's a 1 to 2.5x. So on a 512 meg machine, you're looking at maybe a gig and a half is where you're going to top out in utility. But we're always refining the algorithms. As this gets out in the wild, we'll find more things to do with that cache. So for Vista, 1 to 2.5. As we move forward, that ratio will grow.
Thanks. Looks great.
Thank you. Yes?
You mentioned how the startup items would be given the low priority I/O so they would sort of get out of the way for other things. What happens in the scenario where a user puts something in their startup because it's something that they want to use right away? Like we have a lot of users that will put Outlook in their startup and maybe load up a bunch of calendars of people because that's the first thing they want to use in the morning.
Well, if the user, the beauty of low priority I/O and boxed startup applications, if the user isn't doing anything else, it behaves no differently than standard applications. So in the case where a user has put various applications in their startup folder, they will launch the way they want. But in the case where they're rushing into the office and they've got to print the meeting notes for something that they're already late to, and they want to launch Word and they don't care about Outlook, it's not going to get in the way. So it really is an improvement even for users that are launching custom apps out of their startup folder.
Actually using the startup items for things that they want to put in there.
Right. So I see it as an improvement. Thank you. Yes?
Is there a policy that will allow only Ready Boost to write to USB? I don't want sensitive data walking out of my company on a USB stick. So we don't allow all of our users to use a USB. But if I can get performance improvements by just sticking a USB in,
Right.
why wouldn't I take advantage of that? And I'd need a policy or something that could do that.
Right. We are working with the group policy team right now to finalize that policy on how we can make it so that USB keys are not allowed for data, but they are allowed for Ready Boost. You can also disable Ready Boost if you'd like by setting the service to stop and then using group policy to lock down that service. So the answer is there is no definite answer yet, but we are looking into it.
Thank you.
Thank you. Yes?
I noticed that ReadyDisk seems to be implemented as an extension of the ATA command set.
Yes.
What about all those high-end workstation users who are going to be running SAS drives or SAS arrays?
So for Vista launch, we are not, well, there are two things. One, these features are client features. They're not available by default on server.
Well, this will be workstations.
But so on the workstation side, we do not support RAID with ReadyDrive since it's initially targeted at the mobile platform. It is something we're looking at for future releases of Vista, but RAID is not supported for current versions.
And SAS?
SAS, I don't know.
Okay,
But
'cause that's,
if you want to swing by and give me a card, I will follow up on that.
the other question was Longhorn server. Will these features also be at Longhorn server?
These features will not by default be in Longhorn server. And that's because, by and large, these features deal with the random nature of users, right? Kind of the unpredictable nature of servers. You guys do a great job of tuning them. You add memory, you throw hardware at it, and so you have a much more predictable computing environment.
Software developers, you mentioned, had to make their startup items low disk priority enabled. Is there a way, as myself as a systems administrator, if I have a system that I want to have a startup menu or a startup item automatically run at low priority, sort of like a nice command in another operating system?
Hypothetically.
Hypothetically.
There are other operating systems? No, that's... actually, all of the startup applications are automatically boxed. So that's done for you. The developers of those applications don't have to do anything.
Or any other application that I might.
But we do not have the equivalent of NICE. Well, NICE only does CPU priority. So we have the equivalent of NICE. You can lower the CPU priority in the task manager. We are not exposing the boxing interface through the task manager for this release of Vista. We want to see how people use it. What effect does it have on the OS? We want to tread carefully.
All right. Thank you.
Thank you. Yes?
I'm assuming that Superfetch uses some sort of profiling heuristic sort of algorithm in its mechanism for what it's predicting to cache, etc. Is there ways to tweak that manually and or disable it? Is that going to be part of the configuration, or is it going to be kind of something that you don't have control over?
There are two questions. Is it possible to tweak? No. There's no user configuration. But just like the XP app prefetcher, if for whatever reason you don't see a benefit from Superfetch, there are ways to disable it in the registry. I'd recommend leaving it on, though. Yes?
Hi. I've got an IBM laptop here that's got what they call their active production system. Basically, it's got an accelerometer on the hard disk that will halt or pull the pins back when it detects, the swinging happy joy worker, or, even this movement right here will cause it to happen. What's going to be the effect on, Superfetch and all these different applications with these types of hard drives?
Should have no effect. So it just means that the disk won't service reads and writes while it's spinning, so it's the same as having a blocking I/O.
But what about with the NV cache? Is it going to be available?
That's up to the drive manufacturers. I think it would be fantastic to have both an NV cache and accelerometer. It'll come down to price, as it always does. But that's great because we don't spin the disk down. Notice that in the slides I didn't say 100% of the time ever.
Exactly.
And so for the times when we're not spun down, that's terrific because I bump things. I knock things. I'm the clumsiest PM in the room. So yeah, having those both would be fantastic. I think it'll just be a question of price.
Okay. Thank you very much.
Thank you.
The one thing I saw about the flash cache drives that's a little disturbing is you're saying that the cache is not encrypted. How's that going to interact with BitLocker? And like for the
that's the ready drive does not encrypt the cache. Is probably a better way to put it.
Okay.
BitLocker encrypts the data before it hits the drive. It is fully encrypted. It works seamlessly with BitLocker. So whereas ReadyBoost encrypts data independent of anything else going on in the OS, ReadyDrive doesn't. If that data arrives at the ReadyDrive encrypted, great.
So it stays encrypted then?
Yes,
Okay,
it would be encrypted. Yes.
Same question.
Same answer.
I've actually got another one.
Yes.
Going back to the server question, whether or not any of these functionalities would be available, is a low priority I/O going to be available in Longhorn server or any of the server products?
I don't know on low priority I/O.
Because that's one of them that we
Yes.
would like to have some control over, because we can't know what idle tasks are going to be eating up our I/O schedule.
Yes, I will take that feedback back and I'll have an answer. I'll probably post it on the Longhorn blog.
Okay. Thank you.
Great, thank you.
Question about the ReadyBoost. How dynamic is that? Let's say I have 10 meg of files on my flash drive, and then I want to save another 100 meg. Is that going to just scale down what's being used for ReadyBoost, or?
For this version, ReadyBoost is static. What you would have to do is go into the configuration, reconfigure, and then change then use the rest for your files. But it's a great feature. There's a time constraint. It is high on the list for vNext.
Is it easy to configure, though?
It's very easy to configure. Let me see if I can pop that up real quickly. The reason I didn't demo during the talk is I wasn't sure if I had a device that I hadn't used as a ReadyBoost. Here we go. Removable disk F. Oh yeah, I want to speed up my system. I click. I want to use this device, the recommended 440. We recommend that you reserve about 10% of the device for your own files. Okay. And now when I go to the PFUI, up it goes. It's starting to be used as a ReadyBoost device. That's the configuration necessary. If I want to reconfigure, I'm going to type Windows E to launch an Explorer window. I'm going to right-click on the drive, go to Properties, ReadyBoost. Let's take it down to 342. I clicked OK. You notice a twitch over here. So it dropped down and it back up. So that's how it's very straightforward to configure, both initially and if you want to reconfigure.
All right, thank you.
Sorry, I'm not trying to tease you with the tool again. And again, removing it, no problem. Doesn't affect the system. Next question, I'm going to step back here out of the lights. These things are killing me. I've lost track of which side of the room I was on. I'm going to go here.
Thanks. When Vista goes RTM, do you anticipate that using ReadyBoost alone, it will launch as faster than XP?
Using ReadyBoost alone, keeping Superfetch enabled and all the other OS bits.
Without
That depends.
ReadyDrive.
Boy, that depends on the machine, on the application. There are enough variables that I'm not comfortable answering that blanket, but we will have performance studies coming out with Vista, or shortly afterwards once we RTM, that will address those very scenarios.
Okay, thanks.
So, other questions? Great, well thank you guys very much. And again, please do fill out I was joking about it, but we really do want to get feedback and see sort of, are we addressing your needs as our customers? Thank you.